Serial and parallel data transmission. Today computer is available everywhere, so there is a need of sharing data and other programs among the different computers. Now a user in one part of the world can communicate with a user at different parts of the world by means of computer transmission system. The rise of the internet has had a revolutionary effect on society. One way the internet has transformed society includes the evolution of communication technology that eliminates the obstacle of distance from the communication process. Data transmission. Data transmission is either between two computers, a computer and a peripheral, or between the internal components of a computer. An example includes sending data from one device to another memory, and access to a website, which involves the transfer of data from web servers to a user's browser. Essentially, the following factors need to be considered when transmitting data. The direction of the data transmission, for example, in one direction only or in both directions. The method of transmission, how many bits are sent at the same time. And the method of synchronization between the two devices. Different transmission modes are suited for different purposes, the main one being serial transmission and parallel transmission. So we are going to see first serial transmission. Serial transmission is where data is sent one bit at a time along a single wire. So you have the sender and the receiver. As you can see, data is being sent from the sender to the receiver. So the 8 bits are sent one after another. So as you can see, when 0 will be sent, then 1 will be sent, then 0, 0, 0, 1, 1, 0. So one bit should be sent. After it has been received by the receiver, then the sender will send the other bit. So we need only one line, that is one wire, for serial transmission. This method of data transmission works well over long distances. However, data is transmitted at a slower rate than parallel data transmission. Since only one wire or channel is used, there is no problem of data arriving at its destination out of synchronization. An example of its use is sending data from a computer to a modem for transmission over a telephone line. So it is used for all USB connections to peripherals. Universal Serial Bus (USB). The Universal Serial Bus (USB) is an asynchronous serial data transmission method. It has quickly become the standard method for transferring data between a computer and a number of devices. Essentially, the USB cable consists of a 4-wired shielded cable, and out of the 4-wired shielded cable, 2 of the wires are used for power and the earth, and the other 2 they are used in the data transmission. So now when a device is plugged into a computer using one of the USB ports, what happens? The computer automatically detects that a device is present. The device is automatically recognized and the appropriate device driver is loaded up so that the computer and device can communicate effectively. If a new device is detected, the computer will look for the device driver which matches the device. If this is not available, the user is prompted to download the appropriate software. Advantages of USB. Devices plugged into the computer are automatically detected and device drivers are automatically uploaded. The connectors can only fit one way, and this prevents incorrect connections being made. So USB has become the industry standard as considerable support is available to users. Several different data transmission rates are also supported. And newer USB standards are backwards compatible with older USB standards. Disadvantages of USB. The older USB standard may not be supported in the near future. The present transmission rate is limited to less than 500 megabits per second, and the maximum cable length is presently about 5 meters. Integrated circuits. Integrated circuits are more expensive when they have more pins. To reduce the number of pins in a package, many integrated circuits use a serial data transmission to transfer data when speed is not important. In the initial time, data was sent in serial form, for example 1 bit at a time over a single channel. And with the advent of technology, integrated circuit introduced and allowed multiple devices on a single silicon chip. Because of it, the parallel transmission of data came into existence, and conventionally it uses the transfer of a byte, that is 8 bits, simultaneously making the transfer of data faster. So the standard parallel interface uses a 36-wire heavy cable that was also expensive. So today many integrated circuits make use of serial and parallel data transmission. For example, multiplexers or MUX is an example of an integrated circuit that utilizes both serial and parallel interface. It is a combinational logic circuit. It is used to switch multiple input signal lines to a single output line using a control signal. It works as a multiple position rotatory switch as it is very fast. The input lines are also known as channels. It can be digital using logic gates or analogous using transistors, relays or MOSFET. Parallel transmission. Parallel transmission is where multiple bits are sent simultaneously. As you can see here, we have the sender, we have the receiver, and here as you can see we have multiple lines. Normally it is 8 bits. As you can see we have 8 lines here, and we have bits, that is 8 bits being sent at the same time. So it is being sent simultaneously. So the sender will be sending the bits and the receiver will receive it. So the 8 bits are sent together, and for parallel transmission a minimum of 8 lines is required. Parallel transmission is technically much faster than serial. This method of data transmission works well over short distances. Over long distances, the bit can become skewed. This means they will no longer be synchronized. For this reason, the only common use for parallel transmission nowadays is between the internal components of the computer. For example, communications between a computer and a printer is most often parallel by means of a ribbon connector. Serial transmission versus parallel transmission. Serial transmission is slower than parallel transmission given the same signal frequency. With a parallel transmission, you can transfer one word per cycle, for example 1 byte, that is 8 bits, but with a serial transmission only a fraction of it, for example 1 bit. The reason modern devices use serial transmission is because you cannot increase the signal frequency for a parallel transmission without limits, because by design all signals from the transmitter need to arrive at the receiver at the same time. This cannot be guaranteed for high frequencies, as you cannot guarantee that the signal transit time is equal for all signal lines. The higher the frequency, the tinier differences matter. Hence, the receiver has to wait until all signal lines are settled, thus lowering the transfer rate. One needs to consider crosstalk with parallel signal lines. The higher the frequency, the more pronounced crosstalk gets, and with it, the higher the probability of a corrupted word and the need to retransmit it. Parallel transmission, however, has its own merits. Multiple bits of information are sent at the same time. At identical clock speeds, parallel transfers are faster than serial transfers because more data is being transferred. However, parallel transfers also have problems. Many wires or traces, that is wire-like connections on the motherboard or expansion cards, are needed, leading to interference concern and thick, expensive cables. Excessively long parallel cables or traces can cause data to arrive at different times. This is referred to as a signal skew. So parallel cables that are too long can cause signal skew, allowing the parallel signals to become out of step with each other, that is, it will be out of synchronization. So difference in voltage between wires or traces can also cause jitter. Direction of data transfer. Data can be transferred in either one or two directions. The different methods are Simplex mode. So first we are going to see simplex mode. A simplex data transmission is one which allows data to be transmitted in one direction only. For example, from the sender to the receiver. So as you can see in the diagram here, we have the sender, then we have the receiver, and data is being transmitted in one direction only. So an example of simplex transmission is data being sent from a computer to a printer, loudspeaker system where an announcer speaks in a microphone and his or her voice is sent through an amplifier and then to all the speakers, teletext information where data is broadcast by television companies at the same time as TV pictures, but people do not send back signals from the television to the areas. The second one is half duplex. A half duplex data transmission is one which allows data to be transmitted in both directions, but only in one direction at a time. As you can see here in the picture, we have the sender and the receiver, and data is being transmitted in only one direction at a time. An example is a phone conversation between two people where only one person speaks at a time, or the walkie-talkies. The last one is a full duplex mode. A full duplex data transmission is one which allows data to be transmitted in both directions at a time. As you can see here, we have the sender and the receiver. The sender is sending data to the receiver, and the receiver also is sending data to the sender, and both are sending at the same time. For example, full duplex, they are used network ports on servers, which usually be set to full duplex mode as opposed to half duplex, or a broadband connections on a phone line. Now we are going to look at asynchronous data transmission. Asynchronous data transmission refers to data being transmitted in an agreed bit pattern. So data bits, that is 1 and 0s, are grouped together and sent with control bits. For example, we have a start and end bits. As you can see in the picture here, we have a start bit and we have a stop bit, that is the end bit. And they are control bits, of course, and in between we have the data bits. So this means that the receiver of the data knows when the data starts and when it ends. This prevents the data being mixed up, and without these control bits, it would be impossible to separate groups of data as they arrived. Now we are going to look at synchronous data transmission. Synchronous data transmission sends data as one long bit stream or a block of data. There are no gaps in transmission, that is, each bit is sent one after the other. The receiver counts the bits and reconstructs the bytes. It is essential that timing is maintained as there is no start and stop bit and no gaps. Accuracy is dependent on the receiver keeping an accurate count of the bits as they come in. So synchronous transmission is faster than asynchronous because fewer bits have to be transmitted. For example, only data bits and no extra control bits. For this reason, it is a choice of network communication links. Error detection and correction in data transmission. In data transmission, during the transfer of data, noise and other impairments are introduced. The method used for the detection of these is known as error detection. Error detection helps in data reliable delivery across channels. It also helps in reducing the undetected error probability, for example, the transfer of incorrect frames. Some kind of algorithm is applied before the transmission of data to produce an error detection code that is usually sent over the channel with the data. The receiver applies the same algorithm and generates error code from the received data, then compares it with the error code generated at the sender's end. If both codes are the same, then it means the data received is error-free. Otherwise, the received data is considered incorrect and the receiver acts accordingly. How parity bits are used for error detection. Data transfer also encounters noise and impairments that alter the digital signal. For example, data sent as 1001 can be received as 1101. So to detect this type of error, the parity bit can be used. Parity bit system can be even or odd, and it is the introduction of one additional bit at the start or end of the bit streams transmitted. In even parity system, the number of occurrences of ones need to be even, so you will count the number of 1 and it has to be even, and decide whether the parity bit should be 0 or 1. However, in an odd parity system, the number of occurrences of ones need to be odd, and then you decide on the value of the parity bit. So for odd parity, you count the number of ones. If it is odd, then you will decide whether the parity bit should be 0 or 1. For example, consider the data to be transmitted is 1001001, and it uses an odd parity system. So the parity bit will be 0 since the number of occurrences of 1 is already odd. So when you count the number of 1, 1, 2, 3. So when we count the number of 1, it is 3, and as we are using odd parity, so the parity bit here, it will be 0. Now suppose this data with the parity bit is transferred and the receiver knows that the parity that has been used is odd. The received data block has encountered noise and altered 2. So as you can see here, it is 1001000. So as you can see, this here has changed from 1, it has become 0. So in this case, the parity bit will help the receiver detect an error since it no longer corresponds to the odd number of occurrences of 1. So when it will count the number of 1, so it will get 1 and 2. So the number of 1 is 2. So it will know that an error has occurred somewhere. The parity bits only helps in detecting 50% of the errors. However, in parity detection, there is a shortcoming that it cannot detect the error if more than one bit has been altered. As you can see here, so this the last two here it should have been 0 and here it should have been 1. But when it will count the number of ones, it is 1, 2 and 3. So it has counted as odd parity has been used, it will count it as odd and the parity bit will be the same 0. So it will count, it will say that transmission has occurred correctly. So in this case, no error will be detected.